Check. Hi, this is Matt McCormick. I'm in the Department of Philosophy at California State University, Sacramento, and this is my first lecture on Peterson's Chapter 2, Introduction to Decision Theory for my Inductive Logic II course. It's Philosophy 161. All right, so we've been uh, looking at the research about human rationality, different theories about what rationality is for, about the biases, about the mistakes, about the contours of the way human reasoning works in actual practice. It's a messy affair. Hominids don't think as clean and straight and precise as you'd think, or as you'd want. And they are built out of meat systems after all, and evolution didn't build a perfect sort of reasoning machine, and there's a lot of questions about what it did build it for. The flip side of that discussion about what reasoning actually is in the human organism is, how do we optimally reason? What are the very best ways to make decisions and to reason through a process to come to a conclusion? So you could think of it as that there's the empirical research into how does human rationality actually work. That's the descriptive project. And then this is the prescriptive project. Here's decision theory, here's inductive logic, probability theory, and here's game theory to give us models for how to ideally optimize decisions, how to make the very best decisions. So this part of the course is definitely prescriptive. It comes from mostly 20th century work by a theorist trying to devise a good, clean, consistent mathematical model that captures the things we want to capture and then gives us the theorems, the axioms, the principles, the tools we need to be able to tune up and optimize decisions. Okay, so now in order to uh, formalize our decision-making process, we need to introduce some distinctions. One of the main tools we're going to use is it's a decision matrix. This is an example down here at the bottom is Christopher Columbus's decision whether to sail westward or not. So his actions are along the left-hand column. Every decision maker, you and me and Christopher Columbus, all we're agents, and we choose an action from among choices of acting. We can sail westward or not. We can get the ice cream cone or not. You can pull the trigger in the robbery or not. So the action is something you choose from a set of alternatives. And then the outcomes depend in part on the state of the world. What's the world going to do? So your action is your input that's on the left column, and the states of the world are across the top row, and then the outcomes are the results of your action in the world, where the row and the column intersect. So for Columbus to sail westward, and then if he's right with this geographical hypothesis, for instance, about India being on the other side, then he'll become rich and famous. There is some other land westward. I'll be famous but not rich. That turns out to be what happened. There's no land to the west. Well, he's going to die because he's going to sail too far. So a decision matrix then will typically list the actions along the left-hand column, the states of the world across the top row, and then the outcomes are the cells in the matrix. Usually the actions are along the left, the vertical axis, and states are across the top, and the outcomes are in the cells at the intersection. So we'll get used to that sort of convention, and we'll break up decisions into that kind of template. Okay, so that's Christopher Columbus's decision. Here's another one. Consider the action, get an insurance policy on your house or don't. The matrix at the bottom puts it into the cell form. But it's also possible, and in many cases in decision theory textbooks or in decision theory articles, people have adopted a convention of drawing decision trees, which can capture all of the same information. So this is a decision tree with, at the left, you making a choice from the box, whether to take out insurance or not. And then from those nodes, the circle nodes, there's either going to be a fire or there's not going to be a fire, which results in the outcomes along the far right hand side. Same information, structured similarly, gives us a way to parse it up and figure it out. What we're going to end up doing is looking at some examples of two-player game or game theoretic situations where one person acts and then another person acts and then another person acts. So we get these sort of branching trees, and we can look at all the possible ways your opponent could act, and you can figure out one thing you can figure out is this what's called a sub-game perfect equilibrium. You can look at a simple two-player game and figure out what's the optimal choice to make from where I am, given where these games can possibly go out there in the future. And we've talked about some examples like this when we, at least in my philosophy of mind, I've talked about this in connection with building computer programs that can play checkers, that can play chess, or play Go, for instance. Okay, so there's an action. Then there's states of the world. There's going to be a fire or no fire, and then there's outcomes. If there's a fire, I won't have a house. If there's no fire, then I'll keep my house. And if there's a fire and I have insurance, then I'll lose my house, but I'll get money. And if there's a fire and I don't have insurance, I lose my house and I've got no money. So those are all the possible ways that can unfold, which are all captured in those cells and lets us organize, see, and figure out what the possible situations are. Okay, so another example, actually, this first one just came up for me in my household this week. One of my sons is trying to figure out his schedule for high school, and he's got the opportunity to take either the AP English class or the regular English class. And I was asking him about the details, and it turns out that in the AP English class, if you get an A, it's worth 5 points in your GPA calculation, or if you get a B, it's worth 4 points because it's accelerated. Whereas under a normal English class, an A is worth 4 points in your GPA, and an regular English class B is worth 3 points for your GPA. So what we realized is he thinks he can get a B at least in the AP class. He's a little worried about taking the class with the increased load and all that. But what we realized thinking it through is, oh, well, the worst you can do, if it's true that you can get at least a B, the worst you can do in the AP class is as good as the best you can do in the English class. So the AP English class choice actually dominates. Is this a case of strong domination? It is. Under Peterson's definition of strong dominance, AP English for my son dominates English because you can, no matter the states of the world that unfold, you can always do as well or better by taking the AP English class, if we've stipulated our assumptions and thought about the scenarios correctly. Which again, like this cleared it up immediately as soon as we were able to sort of put it and think it through in terms of the decision matrix. We realized, oh, this is a strictly dominant strategy. And one of the sort of most basic principles in decision theory is that we're striving to be rational. What does it mean to be rational? Well, when you're being rational, the sort of fundamental axiom here is we strive always to maximize utility. Utility is a measure of measure of the good we're seeking, the good things, the things we want, the money, the grades, the GPA, the ice cream sundaes, whatever it is. If you're a decision maker, you're making choices to try to acquire things, and you're trying to acquire them because they have utility for you. So there's things you want out of them. And one of the things we need when we do formalized decision theory is to be able to quantify the stuff we like, the stuff we want, the things we need out of it. So we need to attach numbers to it. Here it's easy. We can just treat GPA as the thing you're after. Like that's you want to contribute, you want to, that 5 is more desirable than a mere 4 for, GPA calculations. Oftentimes it's very nebulous. It can be very hard to figure out, how do you compare weird things? How do you compare a ice cream sundae with, a retirement account? It can be very strange to try to cross compare different categories of utility. But if we can do it, then decision theory can give us the tools to be able to figure out the answers in these kinds of cases. And I was just winging it, trying to think of one about getting divorced, where you either get divorced or not get divorced. Suppose you're in a miserable marriage or a bad relationship. Well, if you get divorced and you find someone new, you won't be miserable. If you get divorced and you don't find someone new, well, you'll be miserable because you're lonely. But the problem is that by staying in the bad marriage, you don't find someone else, but you don't get divorced, so you're still miserable. So at least the way I've carved it out in this choice, getting divorced, you'll always do as well or better than staying in the relationship. You might find someone new and not be miserable. Maybe you're in such a bad relationship that it couldn't be as bad as what you're in. It can only get better from here. And if that's the case, then the decision matrix tells you what to do. But again, like you can see how loaded this is. All of the assumptions I've built into that have to be true. And if they're not, then this answer doesn't work. It's not the right answer. And obviously, your scenarios might be different. You might feel different about your prospects. Okay, so the other thing we need, I've already hinted at this, is that we need a way to scale the utility. We need to be able to put numbers or quantify the amount of utility we're getting. I think I've already talked about this in the first week, but there's typically 2 or 3 ways that people split these up. Ordinal scales are the easiest. Ordinal scale of ranking the things we want for any agent. If you've got a range of possible outcomes, you just get the agent to rate them. You just get the agent to go, well, what's the thing I want the most? What's the thing I want the least? Okay, you rank those as 1 and 0 or 2 and 1. Or if there's a range of 4 of them, rank these, which one do you want most? If on the menu we have apple, cherry, or blueberry pie, what's your ranking there? Mine would be blueberry first, apple second, and cherry third. So given that I rank those 3, 2, 1 in that order, then my decisions in the matrix would unfold accordingly. Okay, so ordinal scales don't tell us anything about the distance between those. If I've got a horrible allergy to cherries, and eating a piece of cherry pie would actually be deadly. Well, actually, I'd rank that really, really low. That would produce a lot of disutility. But the ordinal scale that just puts blueberry first, apple second, and cherry third doesn't capture how bad or how much I dislike or how much disutility there is in the cherry pie. So that's why you need cardinal scales. Cardinal scales, they can either be intervals or ratio scales. And we won't worry too much about ratio scales in here, but interval scales accurately reflect the difference between the objects being measured. Centigrade and Fahrenheit temperature scales are interval scales, and they reflect the distance between the things we're asking about, the distance between 100 degrees and 0 degrees or something. I won't go into ratio scales too much here, but what ratios do is let us sort of attach a fraction to it, that we could say something, for instance, like I only like cherry pie 1/10 as much as I like blueberry pie, or I really, really love blueberry pie and I loathe cherry pie, so cherry pie is 1/100th as useful, 1/100th as much utility that I attach to it as I do the other case. And I give you some examples of these in the first week, I think. For instance, ordinal ranking of ice cream sundae with no cherry, and a root canal comes out to just to be 1, 2, 3, which doesn't capture how much you hate root canals. But on a cardinal scale, you might say, well, an ice cream sundae is 100 good. An ice cream sundae with no cherry, that's almost as good as 98. But a root canal that's awful, that's minus 575. So now I've preserved the order, but now I've added in the range and the distance between them. And now I've got a way. And what happens mathematically, and this all gets really technical, we won't have to worry about it too much, but what happens mathematically is that if I can introduce a cardinal scale and it's right, it will let me do a lot more work mathematically when I start getting into the theorems and trying to figure out what the best decision is to make, or comparing different options. For instance, here's comparing 4 things. I think I might have shown you this one before. Imagine a week's vacation with Brad Pitt. Gunther's 50-50, that's a ice cream thing, with strawberry ice cream and vanilla ice cream, or Gunther's orange and vanilla, or death. On an ordinal scale, you would rank those as 4, 3, 2, 1, and it doesn't capture any of the detail about the distance between them. But obviously, an ice cream sundae is not nearly as good as a fabulous vacation with Brad Pitt. You'd put a huge distance between 20 and 1500 or whatever. And the thing is that if you read one of these scales and go, I don't like Gunther's 50-50 that much, or ooh, I don't like those a lot, or I don't want care about Brad Pitt. Okay, that's fine. Then we just change the scale for you. We just assign some different values to it. And now actually then we're up and running, because if I attach 1,500 units, whatever we're, however we're scaling our units, to a week's vacation with Brad Pitt, and then I give you some sense to calibrate. I go, but I'd only attach 20 to an ice cream sundae, and you really don't like Brad Pitt much, but you'd like a week's vacation that's all expenses paid. You go, oh, well, if an ice cream sundae is 20, then I'd give that 100 or whatever, right? Now we got a scaffolding on which we can start working, and we can start ranking and making choices and figuring out, the proportions of utility that get produced by different decisions. Okay, so which scale we use makes a great difference to the outcomes for some decisions. We're going to do a lot of ordinal ranking, but here's another good example. You find a strange mushroom in your backyard. There's a 1 in 1,000 chance that it's a death cap mushroom, an Amanita phalloides, which results in death within 12 hours if you don't get a liver transplant. Or if it's not one of those deadly mushrooms, it might just be a delicious side dish to go with dinner. All right, so you've got the choice. Do I eat the mushroom and die, or do I eat the mushroom and live? Sorry, I should have put this as this is a different kind of matrix. If I had put die and live across the top, then we could put values on each one of those states, right? But all I want to do here is just illustrate that on an ordinal scale, eating the mushroom and dying, I put very low value on that. So I rank that lower as a 0 over eating the mushroom and living, that's 1. Ordinal scale just means my order is I prefer to live over die. But obviously, I attach a great deal of disutility on a cardinal scale to dying, but I attach only a little bit of utility to eating the mushroom and living. How great is a great mushroom side dish? It's maybe +5 if dying is -1,000,000. Or, whatever, it's open to debate now. If you say, look, a mushroom side dish is at best, worth 5, but dying, that's horrible. That's -10,000,000. There's nothing worse. Okay, fine. Now we've got a way to run the numbers and figure out the answers. And my only point here is that which scale you choose makes a difference on the outcomes for the decision, especially when we start doing expected value theory. So expected value theory is where we'll multiply the probability times the utility and get a weighted average over all the options. And I'll explain more about that in the next lecture and give you sort of a rundown on how that works. But the way you do this is, if there's a 1 in 1,000 chance of dying, how awful is dying? It's -1,000,000 plus 0.999 times how many units of pleasure? It's a +5. And that turns out to be very low in this case. The cardinal ranking gives us an answer. I don't know if I did the math on it. I didn't do the math on it. Ordinal ranking just says living's better than dying. Cardinal ranking tells us, how much worse is it, or how bad a decision is it to eat the mushrooms. Okay, so again, which scale we use makes a big difference on the outcome of the expected value calculation. The ordinal scale here, for example, is the same for all 3 of the other rankings. It doesn't give us information about the distance or the proportions. And this is an example from the book that just does the same thing that I've just discussed. Okay, so we're going to start formalizing decisions. We're going to model them, we're going to quantify them, and then try to make principled optimal decisions. We're going to try to be rational, which means maximizing utility. And there are better and worse ways to do that according to the theorems and the axioms of decision theory. Decision theory, probability theory, and game theory. Game theory is when we're doing it with other people. So we're going to formalize with agents, actions, states of the world, and outcomes. That's how we're going to draw those matrices. And the value of utility, or utility we attach to outcomes, can be measured with different scales. Ordinal and cardinal will be the ones we'll typically use. And that's it. That's Peterson's chapter 2 to get us set up. And then what's going to happen next is chapter 3 is about making decisions under ignorance, which is a case where you're making a decision where you know what the outcomes could be, and you know how much you desire or don't desire, how much utility you attach to the outcomes, but you don't know the probabilities about which ones are going to come about. Turns out there's some principled ways to still make decisions even when you're in the dark about the probabilities. All right, so that lecture will be next.